All right, can you see my screen?
Yep, looks good.
All right, so yeah, so today I'm going to discuss this paper called Representation Learning for Sequence Data with Deep Autoencoding Predictive Components. This is a pretty new paper that just came out at ICLR this year. All right, so the motivation behind it is that most of the current self-supervised or contrastive learning method is based on maximizing the mutual information between the latent representations and the inputs. So one of these very popular approach is called contrastive predictive learning. And just a quick recap, what is CPC? So the CPC framework is basically, it was initially designed for sequence data too. So basically, let's say we have a sequence of inputs, and the encoder is responsible for encoding it into the latent space Z. And then the autoregressive model will be responsible for like reconstructing the context latent representations. And this CT here is basically coming from the autoregressive model, which summarizes the past latent representations. And what CPC does is to model a density ratio, which preserves the mutual information between XT plus K and CT. So XT plus K is basically inputs in the future time steps, and CT is the context summarized up to T time step. And in this paper, they use a simple log bilinear model to represent this density ratio. And the loss is an info NCE loss, which is basically a softmax between the density ratio and also the negative samples, density ratio of the negative samples. So the big X here is basically a sequence of inputs where there's one positive sample from this conditional probability, P of XT plus K given CT. And there are n-1 negative samples from the proposal distribution. All right, so this is CPC, which is pretty popular. However, frameworks like CPC relies on non-trivial selection of positive and negative samples. So there actually lacks a universal principle. So let's think about all the computer vision contrastive learning frameworks we have seen so far. Most of them rely on like augmenting the inputs, the input images, and sampling sampling it as positive or negative samples. And there are also studies that have shown that the MI lower bound might be loose in these contrastive learning frameworks, and it might not be the only reason for its success. So, so basically how you choose the positive versus negative samples is very important for the success of the contrastive learning framework. So if you recall from the Sinclair paper, they have shown that a certain combination of data augmentations actually perform much better compared to other combinations. All right, and there's one information called predictive information. It is an estimate of information for sequence data. So this predictive information, or PI, was proposed in 2001 in this paper. And it measures the MI between past and future windows in the latent space. So you might want to note that it is in the latent space rather than in the input space. And one nice property of PI is that the estimate is exact if the past and future windows have a joint Gaussian distribution. So we will see that this paper actually makes use of this property to estimate the PI in in their work. All right, so let's take an overview or look at what is this framework, Deep Autoencoding Predictive Components, or DAPC. So the principle behind it is that it maximizes the PI between the past and future windows in the latent representations. Right, so again, it is in the latent representations rather than in the input space. And it also regularizes PI objective with a masked reconstruction loss. So let's look at this figure. So let's say this is an input, a sequence input, where you can assume the x-axis is the time dimension and the y-axis is the input dimension. So they mask out certain parts of the time dimension as well as the input dimension, and then pass through the encoder to get latent representations. And yeah, so they basically measure the PI or maximize the PI between the past and the future windows in the latent space. And the decoder's responsibility is to reconstruct this masked portion of the inputs.
Can you briefly give an example just so I can visualize the time dimension and the input dimension, like what sort of data is being visualized?
Okay, here? So I believe this data is audio data. So it's probably the spectrogram or some type of spectrogram of sequence data. Yeah.
So other types of applications, like what other things do they do in the paper? Like do they use video, and then what is the input dimension for video?
So in the paper, they didn't use video. They did experiments on audio, and so basically any time series data can be modeled in this framework. Like for example, one of the experiments is like basically a time series of temperatures.
Okay.
Yeah, so that's also a kind of sequence data, right? And if you are familiar with EEG, then you can also think of this input data as EEG signals, where this x-axis is the time dimension and the y-axis is basically the EEG, yeah, the
like different electrodes.
EEGs, yeah.
Okay, cool, thanks.
Okay, so yeah, let's look at what is predictive information exactly. Let's say we have a sequence of x1, x2, and yeah, these are time steps, and latent representations. Each z corresponds to the input, the latent representation of the input x at each time step. And let's say we have an encoder function ex and a fixed window size t. So the PI is pretty simple. It's basically the mutual information between the past and future windows in the latent space. So yeah, so you can write out PI in this format, where the GT parsed is basically the latent representation of the past window, and GT future is the latent representation of the next T windows. All right, so this PI, because it's a mutual information, so it measures how much knowing G past reduces the uncertainty about G future and vice versa. Right. Okay, but you might wonder, like, how are we going to actually compute this PI? So how do we estimate PI? There are some traditional methods that estimate the joint density P of G past and G future via k-NOR binning. But the cons of these methods are that they rely heavily on the hyperparameters, and it is also challenging to have a differentiable objective. So in this paper, the authors propose an estimation method based on this assumption. So they assume that every 2t time steps form a stationary multivariate Gaussian distribution. So within or under this assumption, the entropy of G past is the same, would be the same for each time step within this window. So we can drop the subscript T here. And G past and G futures entropy are the same within this 2T window under this assumption. So this will give us a pretty nice simplification of the PI. So under this assumption, the PI is basically reduced to this format or this formula, where the sigma 2T is the empirical covariance of the 2T time window. And the sigma T is basically the upper left submatrix of sigma 2T. Yeah, there's a detailed derivation of this formula. So if you're interested, you can refer to the appendix A of this paper. So this gives us a very nice property because it is easy to actually just collect samples of 2T time steps, and we can compute the empirical covariance. And we don't even need to, and it will, once we have the empirical covariance of 2T, we will have sigma T already because it is just the upper left submatrix of sigma 2T. All right. Any questions here? Okay, so this derivation also gives us like a so-called byproduct of PI. So once we have sigma 2T, right, we can reuse it to approximate the PI within T over 2 or half of the time window or 1/4 or etc. As long as the time window we are estimating is larger than 1. So yeah, so how we do it is basically just extract the submatrices, the left upper submatrices of sigma 2T. So we don't need to recompute, we don't need to recollect samples and recompute the empirical covariance. We can make use of the sigma 2T. And another note by the author is that this estimate is invariant to invertible linear transformations in the latent space. So they want to reduce this degree of freedom by encouraging the latent representation to have identity covariance. And you will see this in the final objective function later, that they are enforcing or encouraging the latent representations to have identity covariance. Okay. And one last component of this framework is mask reconstruction. So I'm sure everyone is familiar with BERT. So in BERT, there is this mask reconstruction is inspired by BERT, where they mask out both the time segments and the input dimension. And the objective for the model is to predict the masked inputs. So for example, these white areas here represent the masked out inputs. And yeah, and here is the objective. So basically you want to minimize the norms of the mask, the reconstructed inputs versus the original inputs. And another variant of this reconstruction is a shifted mask reconstruction. So basically, what the latent state or what the reconstruction is doing is to reconstruct a future time frame rather than the current time frame. So imagine you mask out this part, but the prediction is to predict. You mask out a future time frame, but your input is current time frame, and the model is to the model's responsibility is to predict the masked future time frame. Yeah, any questions here?
From the graphic, I also think you mentioned earlier that the network also has to predict not just like certain masked out future timeframes, but it looks like they entirely mask out certain of the y-axis.
Yeah, yes. So yeah, so the masking is done on both the time segments and the input dimension. So let's say this is let's imagine this is an EEG signal. So it basically masks out one entire EEG channel as well.
So do they, I'm just curious, like the effect of the time prediction versus the input prediction, do they do ablations or experiments on how much predicting those two different dimensions helps your final performance?
Yeah, that's a good question. So from what I remember, I don't think they do the ablation study, but they refer to an earlier paper that so the earlier paper found out that masking both dimensions gave better empirical performance compared to only masking out the time dimension. So that's why, yeah, I believe that's why they adopted this method.
Interesting. Okay.
Okay, so this is the final objective. So the first two terms are basically the PI, or the predictive information, where this T/2 is the multi-scale term. And the third term here is the shifted reconstruction loss. And the final term here is the orthogonality penalty. And yeah, they use some hyperparameters to trade off different objectives here. Yeah, and I hope this is clearer now, how this framework works. Okay, now let's move on to some experiments. Okay, the first experiment is noisy Lorentz attractor. So basically the task is to perform dimensionality reduction for recovering Lorentz attractor. So if you don't know what is Lorentz attractor, this is a visualization of it. Yeah, so what they do is they basically lift. So Lorentz extractor, the ground truth is in 3D, right? So they lift 3D clean signals to 30D with an MLP, and they further corrupt the high dimensional signals with certain white noises with different signal to noise ratios. And the task for the model is basically to reconstruct the to perform dimensionality reduction and reconstruct the original Lorentz attractor. And here are the models. The encoder and decoder are pretty simple. They are just bidirectional GRUs. Sorry, the encoder is bidirectional GRU, and the reconstruction is just through a feed-forward NN. And they also compare to previous methods. Yeah, so for example, CPC is the earlier contrastive learning framework. And I believe the last three columns are their methods, but different variants of their methods. So PI only means in the objective, they only use the PI part without the mask reconstruction. And MR means with only mask reconstruction without PI term. And the final column shows the overall, using the overall objective. Yeah, and yeah, I'm pretty impressed by this, actually, by how well this model is able to reconstruct the original ground truth Lorentz attractor. Right.
Looking at the optimal hyperparameters, can you remind me what S and alpha are?
Okay, so, oh, sorry. So this S here, S equals 0 basically means there's no shifted mask. So it's the mask reconstruction is not shifted by any to any future time frame.
So it's predicting the current time frame?
Yeah, in this experiment.
Okay.
And alpha, gamma, beta are the like the weights for this. So alpha equals 0 means they don't use multi-skeleton in this experiment. And beta and gamma are just weights weighing the reconstruction loss versus the, as well as the orthogonality penalty.
Got it.
Yeah.
So there,
Okay.
okay, so beta and gamma here are relatively small compared to the PI term.
Yes, yes.
Okay, cool.
Oh, and T is the time window. So they use a time window of 4 seconds, I believe, or like for this particular experiment. Okay, the second experiment is forecasting. So yeah, they use 3 data sets. They didn't really describe the data sets in detail, but from what I understand, one of the data set is like temperatures or time series temperatures data. So the task is to predict future time steps with different lags, means like how many future time steps you are predicting. And the encoder is also a GRU, and for reconstruction they use linear regression. All right, and yeah, so this figure shows the R2 score for reconstruction, and it is not the absolute R2 score, so it is in comparison to PCA. So I think they use PCA as the baseline. So you'll see a PCA of 0 here, and the red lines are indicate the DAPC, their method, and they compare it to other CPC or other methods here. Okay, and yeah, and this table is just showing showing like how much improvement they gain by incorporating the PI term or incorporating the reconstruction term here. So yeah, so I think I believe FR is the full reconstruction without masking. So you will see that without the full reconstruction results in higher R² scores compared to using masked reconstruction. Yeah. Okay. And sorry.
Do you know, so lag you said was how many frames into the future they were predicting?
Okay, so yeah, so the lag is 5, 10, 15. So basically 5 means 5 days in the future, 10 days and 15 days in the future, or 5 time steps into the future.
Okay.
Yeah.
Cool.
So yeah.
And then I guess they would have hyperparameter tuned that T, S, alpha, beta, gamma for each of these tasks again?
Yeah, I think so. I think they also report hyperparameters in the paper. I didn't put it up here though. Yeah.
Okay, cool.
Okay. Okay, so whenever we talk about sequence data, we usually think of speech or speech data. So they also perform experiments on automatic speech recognition. And these are 2 standard data sets for automatic speech recognition. And in this experiment, they use a transformer-based network. And these are the hyperparameters they show. So you will notice that here they actually use shifted reconstruction instead of a non-shifted reconstruction. And they also did some ablation studies to compare different variants of their methods. So for example, without pretraining, I believe it's just direct supervised classification, and PI only is only using the PI term in the adjunctive, and MR is masked reconstruction only. And yeah, and DAPC plus multi-scale PI is basically the alpha. Oh, sorry, I didn't include the alpha hyperparameter here, but yeah, they also compare whether or not to include the multi-scale term and or DAPC plus both. Yeah, so I think they in their, so when they first introduced shifted reconstruction, they said that empirically they found that shifted reconstruction is beneficial for automatic speech recognition. Yeah, so I think this is what they where they found it by this ablation study. All right, and compared to other automatic speech recognition models, so DAPC reaches a pretty low word error rate. So I think the only model, or the only two model that perform better than DAPC is the wave to vec version 2, as well as this discrete BERT plus wave to vec. So in the paper, the author suspect that it might be because of their much smaller model size compared to this wave to vec. So because they use yeah, so they say their model's parameters are only 30 millions, whereas the wave to vec has 300 million parameters.
Do they for that difference, the fact that wave to vec and discrete BERT, wave to vec are doing better than their proposed method, so efficiency is obviously helpful here. Do they say anything about, like, could you use this loss function somehow integrated into the wave to vec and maybe get even better performance than what wave to vec alone accomplishes?
Yeah,
like, is there some sort of
yeah, I don't remember they mentioned that. And yeah, personally I'm not familiar with wave to vec, so I think yeah, I can look into it and see what this model is exactly doing. Yeah, so this is only just their suspicion. They didn't do any ablation study either.
Okay, do you know the difference between discrete BERT plus VQ dash wave to vec? Like, why does that have a higher word error rate than
yeah,
I guess
sorry,
wave to vec 2.0.
I guess this one is like version 2, so it's probably then
yeah, some magic
yeah,
happens.
I will need to look into these two papers and see what they are exactly.
Okay, cool.
Okay. So another nice thing about the DAPC is that there's a probabilistic interpretation of it. So if any one of you here is familiar with generative models, this is how like they interpret the DAPC in a generative model setting. So let's say we have a generative model where the prior distribution of GP and G future, G past and G future is Gaussian, and the conditional probability will be also a Gaussian. And in this generative model, basically GP and GF generates XP and XF, where XP and XF are the past and future inputs with this decoder or stochastic decoder. So this is the setting of a generative model. But in this setting, or like we only observe X, so we want to infer the latent Z by maximizing marginal likelihood of X. So if we take a variational autoencoder approach, we will parameterize a stochastic encoder E of Z given X to approximate the posterior, right? So yeah, so this is the final objective if we take the probabilistic interpretation of the DAPC. But they did not really give us a detailed derivation of how they reach this this final objective. So if anyone of you here is familiar with like VAE, yeah, I'm happy to like work with you to figure out how they reach this. So basically, in the final objective, there are 3 or 4 main terms. The P hat X here is just the empirical distribution of the training data. And this part here is the reconstruction loss. So you can think of this E of G given X is the approximate posterior. And this term is the chiral divergence between the approximate posterior versus the prior. So remember, our prior is a Gaussian, and the final term is just a PI. Yeah. Okay. And under this probabilistic interpretation, there's a problem of how do we parameterize the covariance sigma, right? So so they claim that simply parameterizing it as a positive definite matrix does not work well empirically. Although they didn't show a ablation study here, but I believe it's from their probably preliminary experiments. So what they did is instead is they use pseudo sequences X star with learnable parameters and compute sample covariance from this encoder. Yeah, so this is how they basically estimate or parameterize the covariance sigma. And just a comparison to the deterministic objective, where we have pretty similar terms here. We have both the PI term, the reconstruction loss, but the deterministic objective doesn't have the chiral divergence term here. All right. And they also performed experiments using this probabilistic variant of DAPC. So on these Lorentz attractor experiments, you can see that the results, I think visually they are a bit different, but by looking at the numbers here, the R-squared scores here, they are pretty close. And the probabilistic variant is also much better compared to the baseline methods. Yeah, and this is the experiments on the future time step or forecasting experiments. So I guess the probabilistic version is that the cons or the drawback of it is that the training is more time consuming and memory intensive. However, it gives us a well-defined generative model. So yeah, so I believe it would be useful in some settings in the future. Yeah. Okay, any questions here? Okay, if not, let me move on. Okay, I guess the takeaway here is that yeah, it leverages the PI, which is like an existing predictive information for representation learning. So I feel that it's a pretty new thing here. And one important difference between the previous CR methods versus this DAPC is that in this paper, the mutual information is explicitly maximized in the latent space within a time window, right? Whereas previous methods maximize the mutual information between current representation versus future inputs. So they say that these methods actually also implicitly maximize an upper bound of MI between the representations, because the mutual information between the latent representations can only be smaller than the mutual information between the Z past and X future. Yeah, and another advantage of this method is no negative sampling is required, and the estimate of PI is exact on the Gaussian assumption. And we also have a probabilistic interpretation that links to variation autoencoder. But some of my questions are, so when they estimate PI, they made this assumption of a stationary Gaussian assumption within this 2T window. They didn't really do ablation studies or experiments on this assumption. So, but just quoting a sentence in the paper, they refer to a prior study that Gaussian-based estimate is a good proxy for the full estimate. So that's why they adopted the Gaussian assumption. And yeah, so I'm hoping that or like from what I have read so far, I hope they can give more validations on this or some ablation studies. And they also didn't really show the effects of time window length because in the objective or in the PI estimate, T is actually pretty important. Like I imagine that different window lengths will result in different estimates, and yes, but they didn't really do any analysis of the effects of different window lengths. So I think they just treat T as a hyperparameter in their experiments. So this is one thing that I hope they can they can show more. All right. Yeah, I think that's it. Do you have any questions?
Yeah, awesome presentation. Thanks for walking through the paper. You work with EEG data, is that right?
Yeah.
So have you tried this, or are you thinking about trying this on EEG?
Yeah, I haven't tried this, but I think this might be useful for EEG since it is a pretty natural fit.
Yeah.
Like EEG sequence data is a pretty natural fit into this framework. Yeah, so yeah, I'm hoping, or I think it could be an interesting direction to try it.
So I don't do much work with sequence data. So from your perspective that, you've worked with all that EEG data, what about this framework is exciting, I guess, or, potentially likely to give you better results than other things you've used for EEG?
So I think EEG, like usually for EEG we have very limited labels, so it'd be good if we can like do some self-supervised pretraining. Yeah, for the model.
And so the naive self-supervised pretraining would just probably be to predict the masked out bits, like not include the
right. Yeah, exactly. Or even more naively would be like you don't mask out. Or I guess it's pretty similar. It's like it's adopted in my paper, where we just simply predict the future time window given the current time window. Yeah, and another nice thing about this method compared to the CPC is that I think for CPC you still need to think about how you are going to sample negative samples, right?
Mm.
Yeah, and I believe in the original CPC paper, in their audio experiments, they sample negative or they did ablation studies on different negative sampling methods. Like for example, they sampled from different audio speakers, or like different types of sampling methods. But it's not like I think it's kind of like a trial and error, and it's different. It will be different for different types of data. Whereas here you don't really need to perform negative sampling. So I think that might be an advantage of this paper applied to EEG.
Cool.
Okay, any other questions?
Okay, I think I'll go ahead and stop the recording.